Alright, now we're going to move on to our turbulent flow. And as I said before, our geometry and our mesh are going to remain the same. All we're going to change is our setup. And now that this is open, we're going to go to our models and make sure that this is viscous Spallert Almaraz. It's no longer laminar or inviscid, and this is the one we're going to use. So once that's done, we're going to go to our materials, which is air, and make that a 1.225 density and a viscosity of 1 times 10 to the negative fifth. We're going to try to make this turbulent flow, so our Reynolds number needs to be pretty high. So this should bring down the viscosity to make our Reynolds number go up. And our Reynolds number I've calculated to be around 3,675,000, which our velocity for that needs to be 30 meters per second. And again, pressure outlet with no reverse flow. And once that's done, we can make our reference values, make sure they're coming from the inlet to update this density, velocity, and viscosity. And we're gonna keep the same method we used for the laminar, which is the coupled one. And let's make sure our laptop doesn't die here. Make sure this is set to second order as well. Our residual, for the sake of the video, we're gonna make it 0.001. And we're gonna initialize this and go ahead and run the calculation. And I'll be back after that's finished. Alright, now that that's finished, we can go ahead and check here our contours. So we can start off with our velocity contour, making sure everything here is selected. And go ahead and display that. We can clearly see here that we have a nice laminar flow over our cylinder. And we can check now our pressure, static pressure contour, and see that it is looking good. And it does. And now we can plot our pressure coefficient on the cylinder wall, which is perfect. Starts at 1, goes all the way down to -2, and then ends up plateauing at around -0.47, which is about what we expected. It's lower than our laminar flow, and we have to make sure that that coefficient of drag is lower. If we go to our forces here on the cylinder wall, we can print it and check here, and yep, it's about half of what we calculated for the laminar, which is good because it should be lower than laminar and higher than inviscid, obviously. And now that that's done, everything is checked for the turbulent and the setup, we can move on to our streamlines to see what those look like in the wake region and over and under our cylinder. So once we get that loaded in, we're going to be able to take a look and see if they match what we have expected theoretically. And so we can check our streamlines here. Once this loads in, I might have saved from the previous run. Once I go ahead and change our view here, still loading. Yeah. Save that from the last one. We can change our. Yep. So you guys can see this more clearly. I'm gonna zoom in a little bit and pan this so you can see it's not actually symmetric, which is good. This wake region is different from the bottom one here. And we did all the exact same things from the symmetry 2 so we can actually see the mesh, or sorry, the wake region there with 750 points. Again, to make sure that this wake region is visible and seen as asymmetric, because again, it shouldn't be symmetric for turbulent flow, especially at the Reynolds number that we have. So that should be it for our turbulent flow analysis. Thank you.